Suppose you wanted to sketch the curve which has this equation in this interval. An obvious first step is to look at the behaviour of two simpler curves. Here's y equals cos 3x. Call that fx. And here's y equals sin x minus e to the cos x. Call that gx. It's clear that f and g are continuous, at least in this interval. But does this mean that f over g, the quotient function you're looking for, is also continuous? Well, if there's going to be a problem, it will be at x equals pi by 2, where both the numerator and the denominator are 0. So, what does the quotient function look like for points near to pi by 2? To the right of pi by 2, both numerator and denominator are positive, so their quotient will also be positive. To the left of pi by 2, fx and gx are both negative, and so their quotient will be positive there as well. But what happens at x equals pi by 2 itself? Since gx disappears there, you might expect that f over g has a vertical asymptote. Well, let's plot some values for f over g. The only point we can't evaluate it at is x equals pi by 2, of course. But it looks from the two sides of the graph as if they should meet there with the value 3. So x equals pi by 2 isn't a vertical asymptote. And the reason for that is because the numerator vanishes as well as the denominator. But we do seem to have a limit. Are we able to say whether this limit does exist? And then, if it does it equal 3?
Let me ask those questions more generally. If you have two continuous functions, f and g, which are both 0 at the same point c, what can you say about their ratio as x tends to c? Does it exist? Can you evaluate it? Well, by the end of the program, you'll have a theorem called L'Hospital's rule, after a 17th century mathematician, Marquis Guillaume de L'Hospital, which answers these questions. And I think it's an amazing result. What you do is take the derivatives of numerator and denominator, and then consider the limit of their ratio. And under certain conditions, which we'll add in later, the theorem says that the original limit does exist, and it equals this limit as long as this exists. Well, that's L'Hospital's rule, and if you use it on the function you've already met, it does give the value 3. I'll be showing you that later on, along with what happens when you try it on this other function. Both numerator and denominator vanish at 0 this time. But if you're going to use L'Hospital's rule here, you have to be really rather crafty.
Well, there's a lot to be done before you can be satisfied that the rule is correct. We're going to go through 3 separate steps in order to prove L'Hospital's rule. We begin with Rolle's theorem, which you've already met in the unit, and although it doesn't seem to have much to do with proving L'Hospital's rule, you'll find that we can build on it to give other theorems that can be used. So just let me remind you of what Rolle said. For a function f, differentiable in the open interval ab, we suppose that f of a is equal to f of b. Rolle's theorem then says that there is some point k inside AB for which f dashed of k is 0. The tangent of the curve at k is horizontal. In other words, the tangent is parallel to the chord joining the endpoints of the curve. Our next step is to look at an extension of Rolle's theorem called the mean value theorem, to cover the general case where f of a is not necessarily equal to f of b. In this case, it's not a horizontal tangent we're interested in, but we're still looking for a point for which the tangent of the curve is parallel to this chord. In fact, it's easy enough to find such a point K if we look at the situation geometrically. We start with a line parallel to the chord, and then we move it in a vertical direction. It will intersect the curve in 2 points, and keeping it parallel to the chord, eventually it will meet the curve in just 1 point. It'll be a tangent to the curve, and the point where it's a tangent gives us the point K that we seek. In other words, it's the point of the curve for which this vertical distance is a maximum. So how do we find that maximum? Well, let's look at it in a different way. Over here, I've reproduced the axes, and I've got just the same interval. And at each point x of the interval, let hx denote just the distance above the chord to the curve. Now, the point we're looking for is one for which h of x is a maximum. In other words, we're trying to find a point where h dashed is 0. But of course, before we can differentiate, we need to know what the function h of x is. Well, in terms of fx, hx is fx minus this distance, x tan alpha plus L, which is just, this is x tan alpha, this is L, the intercept on the axis. So in fact, this is an elementary result giving us the height up to the chord. So now we can differentiate hx, and we get h dashed of x is equal to f dashed of x minus tan alpha. Now remember, what we're looking for is a point K for which h dashed of x is 0. And so that means this is 0, and therefore f dash k is equal to tan of alpha. In other words, the tangent at k has got the same slope as the chord. But of course, we haven't proved anything yet, and we've not shown that such a point k actually exists. But we do seem to be on the right track, because if the point k does exist, then we shall have found a point at which h of x is a maximum. So what do we do next? Well, you see, if we want to know that k exists, we don't actually need to look for maxima. We just need to know that h dashed of x takes a 0 value somewhere. Well, can we prove it does? Yes, we can, because you see, h satisfies Rolle's conditions: continuity, differentiability, and also we have h of a and h of b are both 0. So h dashed must disappear somewhere inside the interval. And since h dash k is equal to 0, therefore f dash k is equal to tan alpha. Now this really is what the mean value theorem says. It's telling us that the tangent is parallel to the chord. And if we look at the value of tan alpha, you see it's just fb minus fa, that's this height here, divided by this base, which is b minus a. Now we've relied on the geometry to prove this result, and just for this particular curve. But if you look in the unit, you'll find a rigorous proof applying to any suitable curve. Well, that's 2 theorems dealt with, and we're already halfway to the proof of L'Hospital's rule. But we still don't seem to be very close to it. It's the next theorem that brings us a lot closer, and we're now able to tackle that. We need to look at the parametric plane, because if you look at the equivalent theorem for that plane, you get a ratio of 2 functions.
In the parametric plane, curves have their coordinates described by independent functions ft and gt. In other words, curves result from plotting points for different values of t. So you can think of the curve as representing the path of a particle going along the curve from one point to another. You can think of t as time. Let's call the beginning t equals a and the other end t equals b. It's the same sort of theorem again. Here's a chord joining the endpoints. Once again, there is going to be at least one point on the curve where a tangent to the curve is parallel to this chord. Call such a point t equals k.
What we've got here geometrically is another mean value theorem. The slope of the chord is now fb minus fa, that's this height, divided by gb minus ga, that's this base. The Cauchy mean value theorem gives a version of the mean value theorem for curves given in parametric form. It says that there exists a point k such that the tangent slope equals this expression. Well, how would you work out the slope of a parametric tangent? The tangent's the limit of chords through the point t equals k in this case. And the slope of the chord is this height divided by this base. So you can work out the slope of the tangent as this completed limit, where you divide the height, that's this expression, by the base, that's this expression. And I can divide all the top expression by h, so long as I do the same to the denominator. The limit can, of course, be expressed as a quotient of two limits. And so now the numerator is our familiar definition of the derivative f dash k, and similarly the denominator is g dash k. So the tangent slope at k is f dash k over g dash k. And this is what's needed to state the Cauchy mean value theorem fully. I've given you the idea of the proof geometrically. The rigorous proof is in the text, as is just too algebraic to do here. But here is the formal result. And at least this bit is reminiscent of L'Hospital's rule.
But how does such a mean value theorem for parametric curves get us closer to solving problems of the general type we started the program with? The condition was that f and g should vanish together at some point c. Well, in the parametric plane, f and g vanish at the origin. Call that the point t equals c. So we've only to consider the special case of parametric curves which actually pass through the origin. Any results which we obtain in this case can be used to tackle our original problems. So whatever our curve is, it must go through the origin and then on maybe something like this. Suppose that the beginning of the curve is now somewhere over there at t equals a. Well, what else can we say about it? The curve passes through the origin when the parameter t is equal to c. If you think of t as time, the part of the curve from a to c corresponds to points earlier than c. We continue to follow the curve through points later than c as far as the point b. Let's look at that part of the curve first and see what we can say about the chord joining the 2 points c and b. We can apply Cauchy's mean value theorem to find a point t equals k in the interval cb where the tangent is parallel to the chord. We then have f dash k over g dash k equal to fb minus fc over gb minus gc, just as before. But now, of course, we're subtracting fc and gc, both of which are 0. And so what we get is just f dash k over g dash k equal to fb over gb. Now imagine that b moves closer and closer to c, and the chord itself will move closer and closer to the tangent at the origin. And also, as b decreases towards c, the point k will get pushed ever closer and closer to c. In fact, b and k tend to c plus together. Now this equality always holds throughout the limiting process, as k and b tends to c plus. Now if we suppose that this limit of f dash k over g dash k as k tends to c plus exists, then it must follow that the limit of fb over gb as b tends to c plus must also exist, and in fact they'll have the same value. Notice that b and k have now assumed the same role, just that of a variable approaching c from the right. So we might as well replace each of them by the symbol t. This limit is then the limit as f dash t over g dash t as t tends to c plus. And similarly, this limit becomes the limit as t tends to c plus of ft over gt. In fact, if this limit as t tends to c is known to exist, then both these two one-sided limits are known to exist, and they must be equal to it. Has this proved L'Hospital's rule? It certainly looks very promising, but don't forget, these are all right limits. Well, you can use exactly the same argument to get the corresponding result with left limits. If this limit at the top here exists, then these two left limits here must exist and be equal to it. So what does that give us? Let's bring the two separate results together and see what we've got. Because now you see, if we know that this limit at the top here exists, then we can deduce that all of these one-sided limits exist, and they're all equal to the limit at the top, so they're all identical. In particular, since these two one-sided limits exist and are equal, we know that the limit as t tends to c of ft over gt exists. Of course, it's equal to the common value. Let me rearrange this a little to give the result we promised you at the start of the program. So that's L'Hospital's rule. Usually the result is stated in terms of x rather than t. If the functions are differentiable in an open interval, then the rule holds at any point c in that interval at which both functions vanish.
Well, we can now deal with the first of our two problems. The numerator and denominator both vanish at x equals pi by 2. So L'Hospital says that the limit is this. The limit as x tends to pi by 2 of this, the derivative of cos 3x, divided by this, the derivative of sine x minus e to the cos x, so long as this limit exists. And because the numerator and denominator are both continuous at pi by 2, our limit exists and equals the value of the quotient at x equals pi by 2. That is 3 over 1, or 3. Well, that was very quick. But as I said, the second problem is more tricky, and I'm going to solve that at the end of the program. But first, let's have a quick resume of how we derived L'Hospital's rule, followed by a different way of looking at what the rule says. We've had 4 theorems, so let's remind ourselves of each of them. First of all, Raleigh's theorem. That said that if fa and fb equals 0, then there must be a point inside the interval ab with a horizontal tangent. Then Roy demonstrated the mean value theorem, which generalizes Raleigh, where fa doesn't necessarily equal fb. There is still a point k at which the tangent must be parallel to the chord. But these theorems are for functions of the type y equals fx. And here's the next two. This third step was the Cauchy mean value theorem. That brought us immediately closer to quotients by looking at the mean value theorem for curves given in parametric form. Then Roy, from looking at the special case where a parametric curve passed through the origin, was able to prove L'Hospital's rule. That states that the limit of our ratio, f over g, is equal to the limit of the ratio of the derivatives if that exists. Those are the 4 theorems in the program. And following the same idea of looking at things geometrically, let's have another look at problem 1. Here are f and g again, but this time with the tangents drawn in at c equals pi by 2. If you look close to pi by 2, you find that the tangents closely approximate the curve. And because these triangles have the same base, you find that the ratio of f over g is more or less the same as the ratio of f dash over g dash, and that looks as though it's 3 to 1. Well, of course, it was the geometrical picture which guided mathematicians like Lhospital. In fact, wouldn't it be intriguing to be able to look over Lhospital's shoulder to see the way rules such as this were proved in the 17th century?
Imagine that I've stepped into Lhospital's shoes for a moment. Probably it all began with something sketched out on the back of an envelope. He would have started with something like this, something he already knew. Now, of course, his notation would have been different from ours, but in essence it would say the same thing, that the limit of this ratio is f-c, and the limit of this ratio is g-c. What he did next was to change these limits into approximations. So now he has approximations to the slopes of the tangents at the point C. Now it looks very tempting to divide these two one by the other, and so get rid of the x minus c's and obtain this approximate value for the ratio. And then, because fc and gc are both 0, he surmised that he could go back to the limit and get the limit as x tends to c of fx over gx equal to f-c over g-c. That was more or less how Lhospital arrived at his rule. Back in the 20th century, it's known that arguments like this can very easily break down. Lhospital was lucky. His conclusion is correct, even if his method of proof leaves something to be desired.
Well, Lhospital's rule helped us to evaluate the limit in problem 1. Can it help us here too? If this is our f and this is our g, we find both vanish at x equals 0. But we know what to do. Lhospital to the rescue. Surely all we need to do is to find the limit of f dash over g dash and evaluate it. That's this. But evaluating f dash over g dash gives us an undefined limit again. So, are we now stuck? In fact, we aren't. You see, we can apply Lhospital's rule more than once. This is the limit of second derivatives. And that is defined at x equals 0 to be 2 over 1. So this limit exists and equals 2. You see, it's quite acceptable to apply Lhospital's rule several times if, each time you apply it, you find that the new quotient also has a numerator and denominator vanishing together. And if you finally reach a ratio that does have a limit, you can argue backwards, as here. If the limit of f double dash over g double dash exists and equals 2, then the limit of f dash over g dash exists and equals 2, and the limit of f over g, our original quotient, exists and equals 2 as well.
Remember, all of this applies to the situation where we have continuous functions f and g differentiable in an open interval and vanishing together at some point of that interval. And in those circumstances, Lhospital rules.